morning. We continue with phase separation in liquid mixtures. I've been mainly focusing on thermodynamics last lecture, and now we continue with a statistical mechanics approach. So I will first talk about a lattice gas model. So what we do now is, instead of thinking about this as a density and a continuum, let's imagine we have a lattice. And on this lattice, say a square lattice, as you see here, there are two particles. They could be two different particles, A and B. They could be solute and solvent. And then now we start mixing them, and we want to know how would we start describing that in terms of statistical physics. And the idea really is to derive the free energy from the microscopic interactions so that you can see how the various terms in the free energy density are linked to more molecular scale. We do this now in the following. Like in a Ising model, we assign to each lattice side I a occupation number, not a spin. So we say the lattice side is occupied if this variable sigma I is 1. And we say the lattice side is empty or occupied by a different particle if Si is 0. So for example, here you could read as Si1 blue and Si0 you could read then green. Okay, so and that then, as you take it together, as a configuration of all lattice sides, we call this a lattice configuration, or simply just a configuration. So we need to now assign an energy to that, and you can write this as a free energy density, a free energy or a Hamiltonian. This is just words at this point, because what I mean is I want to describe the system in terms of the energy cost for distributing a certain configuration on my lattice. So what I will need to do is I need to sum over all lattice sides, and now we assume that we have nearest neighbor interactions, and Ij bracket denotes a nearest neighbor pair. So for example, 1, 2, which would be equivalent to 2, 1. So I sum over all nearest neighbor pairs, and then I'm accounting for the different kind of interactions. I have interactions between the particles that are called the solute, and let me call this interaction epsilon pp. Okay, and I have such an interaction if there is a solute particle at side I, and if there is a solute particle at side j. Okay, so if this is 1, 1, then I count this as a energy contribution epsilon pp for that pair of sites. I can do the same for the solvent. So let's think of this, say, as the blue particles. Then I'll count that if there's a solute particle. That means if there's no a solvent particle, if there's no solute particle, and that's indicated by 1 minus Si and 1 minus Sj, and that's 1, 1 if Si and Sj are both 0. Okay, so that's what you have for pairwise interaction between solute and solvent particles. And now we can also have interactions between the solute and the solvent particles. And this can happen if either side I is a solute and J is a solvent, or vice versa. So I have to add those two terms. That's sigma I, 1 minus sigma J, plus the other way around, sigma J, 1 minus sigma I. Okay, so that's our energy or our Hamiltonian with which we want to do the analysis. And then you know once you have a Hamiltonian that you get the partition sum set as the sum over all the distinct configurations of occupations on that lattice sites, and I have to sum over minus beta times the Hamiltonian, which is a function of the different lattice configurations, and as usual, beta is 1 over the temperature scale. Good. Now, how would I evaluate that? Well, let's think of a case first where you have no interactions, right? Just particles distributed in space, but respecting the fact that you have site exclusion, meaning at a particular site you can either have blue or green, but not both, right? That's what I have here. So no interaction. Other than site exclusion. Then the only term that contributes to the partition sum is just counting how many states you have. Okay? So for that, I need to count the number of states, omega. That's the number of states that you have for, say, having a fixed number of solute particles and a fixed number of solvent particles. Well, how do you count this? This is, you have to distribute NP particles on the lattice of total number of n sites, so you have to choose NP from n. And that means that the number of states that you have is from the total number of lattice sites, I'm choosing NP, and that's just the standard expression for the binomial. It's the factorial of n total times the factorial of the number of solute particles, and then times n tot minus np, but that's the number of solvent molecules. Okay, so that's very simple, just counting. And then you know from elementary statistical mechanics, so from a bachelor's, that the Boltzmann entropy is the Boltzmann constant times the logarithm of the number of those states, log of omega. And then let's assume that we have NP and NS both being quite large numbers, such that I can evaluate the factorials using the Stirling formula. And when you do that, what you get, that this is then minus n total times the Boltzmann constant times phi log phi plus 1 minus phi log 1 minus phi, where I defined the phi to be, as before, NP over n total. And note here that now solvent and solute particles do have the same kind of a volume fraction. That's how I define the lattice. They all occupy one lattice site, so they have the same volume fraction. And then the volume fraction of the solute particles simply is the number of those solute particles divided by the total number of lattice sites. Okay? And that's a quite famous formula. It's the formula for mixing entropy of two different particles, which is always phi log phi, and then the complement 1 minus phi log 1 minus phi. Okay, so note that because of our assumption of incompressibility, that the volume fraction of the solvent is just 1 minus the volume fraction of the solute. So this is 1 ns over n total. Okay, and S is called the mixing entropy. And when you look at it, when is this mixing entropy maximal? This is when phi is a half, right? And it becomes smaller and smaller the more you deviate from equipartition between the two species. I can show you that on a graph. So this is what we just did. So this is here the mixing entropy with a minus sign, because later on we need it as a free energy where it comes as minus S. And I divide by the total number of lattice sites, and I take it all in units of KB. And then all I'm plotting here is minus phi log phi minus 1 minus phi log 1 minus phi, and that has this parabolic-like shape where you see that the minimum that you get in the negative entropy is at phi equals to a half. But note the system has no freedom to relax in that landscape, right? Because phi is fixed externally. That's your volume fraction that you define. And then you have to ask, for a given volume fraction phi, what is the value of this mixing entropy? Good, so far so good. This is just a non-interacting system. Now let's talk about what happens as you add interactions. So with interactions, this is in general not an easy problem, right? Because you would need to evaluate the partition sum for the interacting system, which, as you know, is hard. It's a difficult problem. What we will do, though, is we kind of coarse grain and we take a mean field picture. So just imagine when I go back to the slide, when you look at such a lattice gas on the right-hand side, imagine now that you consider a certain volume element, like so, which I traced out with my laser here. And in this volume element that we have here, we take a mean field approach, so we replace a particular configuration that you see here by a mean configuration. So that's what we do. That means we replace the Hamiltonian for a given spin configuration by a Hamiltonian where the sigma i's are replaced by the mean value, which I just indicate with the letter phi. Okay, and I call this here the mean field energy of a given configuration phi. And that you can easily write down, because then from the formula that we just have underneath, so this one, all we need to do is we replace all the local values by their mean values, which are phi. So I get for the interaction, oh, let me just write here the number of interactions that I have. So I have a lattice with a certain number of neighbors, so 4 in 2 dimensions and z equals 6 in 3 dimensions for a cubic lattice. In my volume that I consider, I say I have n particles, and I have a half because every pair is counted just once, and that's what I need to do when I don't want to overcount. So that's the number of pairs that we have here. And for the pairs, the average number of pairs which are given by a solvent molecule, I have to account for the likelihood to find a solvent molecule, which is phi. It's the volume fraction that I have in there. So I have phi squared, or I replace sigma I and sigma j by phi. Same thing. For the solvent interaction, well, I have 1 minus sigma, which I replace by 1 minus phi squared. And then for the interaction between solvent and solute, I have 2 terms which are identical, and they're both phi times 1 minus phi. Right, so reading it again is like saying the likelihood to find 2 solute particles is proportional to their volume fraction squared. I have that energy. The likelihood for 2 solvent molecules to meet is 1 minus phi squared. And for a pair to meet, it's the likelihood of having a solute times the likelihood of having a solvent. And here I have a factor of 2. All right, so that's the mean field expression. And then we say we approximate the mean field free energy just in the following way. So we have this sum over all the configurations, exponent to the minus beta h, and we replace this by a sum over all sigma, where instead of writing the full Hamiltonian, we write the mean field expression as a function of phi. And then you get the mean field expression as a prefactor, e to the minus beta e mean field, and the sum over sigma gives you the log, gives you the number of states. So this is then given by the number of states, exponent minus beta e mean field of phi. And that means my mean field free energy is minus kBt, the log of the mean field expression for the partition sum, which is nothing but the mean field energy of a given configuration with mean volume fraction phi for the solutes, and minus kBt log of omega. Okay. What I want to do is I want to rewrite this expression a bit that we have here and order the terms that we have in the above expression, such that I order it to powers in phi squared, phi, and constants. So let me do this. Mean field expression is the number of pairs that we have, and then we do have epsilon pp plus epsilon SS minus 2 epsilon PS times phi squared, collecting all the terms proportional to volume fraction squared. Then there's a linear term, C1 phi and C2 as a constant, which I don't specify here. You could, but the only term that you will see later plays a role is the one that's quadratic in phi squared. So what you see there, let me remove this, is that in the phi squared term, I can define an energy difference. And this energy difference is the energy of interaction between solutes plus the interaction between the solvents minus 2 times the mutual interaction between the two. This is delta E. Okay, and this can have different signs. It can have the sign that it is negative, and that means you favor attraction between the solute molecules, right? Because then you lower the free energy by increasing the density of the solute molecules. And the opposite is true if you have delta E being positive, and then you would have a repulsion between the solute particles. Note, for that, what has to be negative is not each individual term, but the difference. Okay, so in principle, all these terms can be negative, and you can still have delta E being less than 0. So this may be a bit counterintuitive to you because it says even if the interaction between the solute molecules is negative, you can have effective attraction between the two because there's this additional effect that arises because you have solute-solvent interaction and solute-solid interaction. So effectively, you have to have a configuration where neighbors of solute molecules are favored. All right. So now from that, what we have is a free energy density now. This is all considering the whole thing. So in principle, I should here actually write n total. And here as well. But what I want is I want this for a small volume element, right? And then I read this just for the small volume element. And then the density is kBT for the free energy. And I divide by the volume of our lattice sites, V, because I want a density. That's why I have to do that. And then I simply write the expression that I found, which is phi log phi plus 1 minus phi log 1 minus phi plus chi times phi 1 minus phi. With chi being defined as minus set over 2 times delta epsilon over kBT. Okay. And the way I wrote this is that there are additional terms which I neglect. Those additional terms, and you have to remember this now for remainder, that they all of the structure are constant, which doesn't matter anyway in all of thermodynamics because you can shift energy as you like. And there's a linear term that I ignored as well. Okay? And you'll see later those terms, they don't matter. All right, this parameter has a name. It's named after Flory and Huggins that first came up with such a reasoning for the free energy density of a binary mixture. Okay, so we have two very different terms. This comes from mixing, which likes to have a state where you have no clumping of particles, but distribute them out in an even fashion. This is a term that favors aggregation because you have interaction between the particles. Okay? So it's this balance between a mixing term and a term that potentially favors demixing because of an effective attractive interaction between the two particle types. Okay, now let me show you how this looks like. So before, we just had the term coming from entropy, and this was this parabolic shaped part of the free energy density. And now I just added the Flory-Huggins term. And then you see as you change the chi parameter, the Flory-Huggins parameter, between a low value, which is 1, could also put it 0, and a value that goes to 2 and then to 3, the landscape of the free energy density changes qualitatively in a fashion that you already know. It changes such that for low values of chi, you have a single minimum in the free energy density, and at a threshold value, a critical value of chi equal to 2, the shape changes to one where you have two minima of equal depth and a maximum in between. Okay? So, and as you know, because now the free energy density goes from convex to having concave region, this implies that at chi equal to 2, there must be a phase transition from a state that is demixed to a state that's now mixed. So we see here as chi critical equal to 2, we have a phase transition to a demixed state. We can go even further, and that's just now really recapitulating what we learned in our last lecture, where I told you that there is two characteristic lines. One is the spinodal line given by the inversion points, inflection points here of the free energy density, so here and there. And as you concatenate 4 different values of chi now, these inflection points, you get the dashed line that you see here. And that line is easily calculated, so let's do this on the board. So the spinodal is simply given by the second derivative of phi spinodal equals to 0. And that's not such a hard thing to do. So you have here this free energy density. You take the second derivative, set it to 0, and solve the resulting equation for the chi value. And then you find chi equals a half 1 over phi times 1 minus phi. We also know the critical point, right? The critical point is this one here that we can also easily determine. So let me write this down as well. The critical point is the one where the first derivative is 0 and the second derivative is 0, and this gives you chi critical pair as a half and 2 as we saw from the figure. Right? We still have the binodal. What's the binodal here? So binodal is where you have the tangent construction giving you the regime between which values you have demixing in the system. And that's simple here now. In general, it's not, because you have this common tangent construction. The common tangent you have is very simple here. It's just a horizontal line. So all you have to solve is for f prime at the binodal being 0, and you're done. Right, so this is f prime equal to 0. And when you solve the corresponding equation, you get the chi of the binodal is 1 over 1 plus 2 phi, the log of 1 minus phi divided by phi. And then together we have what I show you here on the slide. We do have the binodal delineating that regime of phi values where the homogeneous steady state is really unstable to any small perturbation. And then between the spinodal and the solid line, which is the binodal, the system is metastable. You need a finite perturbation to kick the system out of the homogeneous steady state, but still, in the long run, it will converge to a thermodynamic state given by the common tangent construction. There's one more thing I wanted to do now. We did not account for spatial heterogeneity in our free energy function. And remember, last time I wrote down just a term that accounts for that, and I want to do the same thing actually here as well. So if you start from the Hamiltonian as a function of sigma I, you can show, and this is in my lecture notes, please read about this. You can show that in the coarse-grained limit, this will give you a contribution in addition to what we have, a term that scales like so. And then you have an integral, say, over the three-dimensional volume divided by v. And then you have a term which goes like a squared over z, and then the gradient of sigma of r squared. And as you will see in the notes, this is not very difficult. Basically, you write the Hamiltonian that we wrote and do a Taylor expansion. And this Taylor expansion gives you a difference term, sigma I minus sigma j squared, and that gives rise to this gradient term. Okay? I didn't want to do this explicitly because it's a kind of boring calculation. And on top of it, you can again say, I don't worry about a microscopic derivation. I can just say this must be there by symmetry reasons. And the symmetry reasons are, if there are gradients, in general there will be gradients, the only way I can account for those gradients is that in the Hamiltonian they have to be scalar. So the gradients have to appear as even powers of, or powers of gradient of sigma. And because of rotational symmetry, that's the only term I can actually write down. So that means when in the end we want to have a coarse-grained description of our system, where instead of a lattice variable, we have a volume fraction as a function of position, what we should write down is a free energy functional that depends on this density as a function of points r in three-dimensional or two-dimensional space. And this free energy functional is an integral over space, and then we have here a free energy density f of phi, and in addition there's a term that is penalizing any kind of gradients that you might have in your system. Okay, and this term C here is given by it's given by kappa over V. And this is proportional. That's the important information I want to give you. It's proportional to the chi parameter as well. Because in the end, the chi parameter is accounting for the interactions. So if I have a profile that's deviating from homogeneity, I will have changes in the composition, and that will have a scale of interaction that's the same scale as the one we had it before, which is the Flory-Huggins parameter. So this is called a Ginzburg-Landau free energy functional. And you can tell me which term corresponds to what. This term is interaction. This term is interactions plus entropy. The interaction term in f of phi is the one with the Flory-Huggins parameter, and the entropy term is this one. Okay, and then the partition sum in that case would be set equals to, now I have to integrate over all different configurations, which is now a continuum of functions, density functions, and the integral has a weight given by a Boltzmann factor, and this Boltzmann factor contains the Ginzburg-Landau functional as dependent on the corresponding density. Good. Questions? Right. We had this before for the Ising model. It's a similar reasoning. There I only used symmetry arguments, and now I gave you a little more detailed approach where I'm not just using symmetry arguments, but actually a lattice gas model that I coarse grain, and then I arrive at the same type of functional. Good. Now that we have that, I wanted with you to write this differently, because that's what we need after the break. Okay, so when you look at the free energy density, it is not really looking like this one, but close to. Right, so remember from what we looked at, we had a single minimum, then as a function of chi, it would develop into a double well potential. This here is a free energy, which we had before in the context of the Ising model, where we had an expansion of the magnetization of the free energy density in terms of magnetization as a parameter r/2, magnetization squared, plus u/4, magnetization to the fourth. I don't have a magnetization in a binary mixture, but I have a density, and I can expand the density around the point, which is the critical point that we calculated before, that is given by phi c equals to 1/2, where a corresponding value translated into density would be chi c, and then you have the molecular volume appearing there. So you can say, let's approximate the function that we have as one where we expand the free energy density around this critical point. And you will see in a second, if you do that, if you expand this function here around that critical point, then you get a quadratic term and a fourth order term. So let's do that before we close. Phi c equals to 1/2. And we have chi c equals to 2. And then we define delta phi as the deviation from this critical value. And then writing out our free energy density as a function of phi, you get a spatial integral over r divided by the molecular volume. And then as you do the Taylor expansion, the first term that you get is this one. You get something that's quadratic in the deviation from the critical value, and it has exactly the value, the prefactor that you should expect, because before in the graph we saw that chi c is the point where the function switches from convex to concave, and that's exactly what happens here. As chi is equal to 2, the parabola that we have here turns from opening up to the top to opening up to the bottom. So you see this again here. And then as you do the Taylor expansion, the next term is one that's fourth order in delta phi, and the prefactor turns out to be delta 4/3. There's higher order terms, and there's a term 1/2 kappa twiddle gradient of delta phi squared. Okay. Good, and with that, we go into the break, and after the break, we will use this expanded free energy to do dynamics, linear stability analysis, and see how the system goes from initial homogeneous steady state into a thermodynamic ground state.